Hi, welcome to InfiniBand Architecture training session. In this video, we will go over the InfiniBand architecture and see how it serves accelerated computing applications by enabling low latency, high bandwidth, and reduced number of CPU cycles. Hence, enabling high performance and efficient scale-out of compute systems. The InfiniBand architecture is divided into 5 layers in a similar way to the traditional TCP/IP model, though there are many differences between InfiniBand and IP networks. Traditionally, applications relied on the operating system to provide them with the communication services they need. InfiniBand, on the other hand, enables applications to exchange data across a network without directly involving the operating system. This application-centric approach is the key differentiator between InfiniBand networks and traditional networks. Now, we will see top-down how each of the layers contribute to the fast and efficient data transfer required by accelerated computing applications. We will begin with the upper layer. Applications are the consumers of the InfiniBand message service. The top layer of the InfiniBand architecture defines the methods that an application uses to access the set of services provided by InfiniBand. The upper layer protocols present a standard interface easily recognizable by the application. Some of the supported upper layer protocols are MPI, Message Passing Interface, a library interface for distributed parallel computing, Nickel, NVIDIA Collective Communication Library, RDMA storage protocols, and IP over InfiniBand. Next, let's move on the transport layer and see how application messages are transported from source to destination. The InfiniBand messaging service is different than the one provided by the traditional TCP/IP, which moves data from the operating system in one node to the operating system in another node. InfiniBand provides hardware-based transport services implemented by the network adapters, also known as HCAs or host channel adapters. An end-to-end virtual channel is created connecting two applications that exist in entirely separate address spaces. Once an application has requested transport of a message, it is transmitted by the sending hardware. When the message arrives to the receiving hardware, it is delivered directly into the receiving application's buffer. Could you imagine messages flying through the network having ultra-low latency and almost zero CPU utilization? Awesome! Until now, we talked about the end nodes, but probably there is a bunch of networking devices connecting those nodes, such as routers and switches. InfiniBand routers are used to connect between different InfiniBand subnets. This allows network scaling, traffic isolation, and usage of common resources by multiple subnets. The network layer describes the protocol that allow routing of packets between different subnets. Routers use network layer addresses called global IDs or GIDs to route packets to the destination node. But what if the packet is routed in the local subnet? How is switching between end nodes in the same subnet handled? This exactly leads us to the link layer. Each node in a subnet is assigned with an address called the local ID or lead. Leads are assigned and maintained by the subnet manager that manages the subnet. The switches' forwarding tables are populated with entries that map destination leads to exit ports. Those forwarding tables are calculated by the subnet manager and programmed in the switch's hardware. When a packet is generated by an end node, it includes a source lead and a destination lead. When the packet arrives to a switch, its destination lead is matched against the switch entries and sent over the respective exit port. Another key element of InfiniBand is the link layer flow control mechanism. Flow control mechanisms are used to adjust transmission rate between a sender and a receiver so that a fast sender does not overload a slow receiver. The sending node dynamically tracks receive buffer usage and transmits data only if there is a space for it in the receiving node buffer. This is what makes InfiniBand a lossless network. Packets are not dropped in the networking during normal operation. Lossless flow control leads to very efficient use of bandwidth within the data center. All those mechanisms sound great, but eventually data transfers occurs when bits are transmitted over the physical medium. The physical layer specifies how bits are placed on the wire and the signaling protocol of what is a valid packet. In addition, the physical layer defines the characteristics and specifications for copper and optical cables. Aggregating multiple physical lanes allows to provide higher bandwidth. Wow! We went a long way to transmit a message between a sending application and a receiving application. We have covered the different layers of InfiniBand architecture and so how each layer provides efficient utilization of compute and networking resources. The high-performance bandwidth combined with ultra-low, near-zero copy utilization enable efficient scale-out of compute systems. In this session, we have introduced the basic layers of the InfiniBand architecture.